Hello, can you hear me? Oh, okay. So can you see my screen? Can you see my screen? Oh, okay. So good afternoon, all the students who are attending these live sessions. I'll be just briefly discuss about the first 2 weeks lectures what we covered. The basically, if you look at basic idea behind to develop first 2 weeks lectures are to interest to really bring the interest about the fluid mechanics for the students level. That's the reasons a lot of example illustrations are given, and what are the type of classifications we do in a fluid mechanics so that can be simplified. Those things we discuss it. No doubt, as a beginner of the fluid mechanics, it may be looking a difficult, but idea was that the basic, the fluid flow classifications, if you know it, you can know what type of fluid flow problems you are addressing it, what are the assumptions behind these, the fluid flow problems, what you are solving it. For examples, if I talk about the flow is incompressibles, that means it indicates for us the one of the flow variables, which is the density, doesn't vary significantly as compared to the density variation is quite negligible. So we can consider it assumed to be a constant. So those are conditions, the flow conditions when we have, that is a flow is incompressible. Same way, if you talk about that the fluid flow problems, if I'm solving it, and the time components doesn't play much bigger roles or doesn't control the flow concept, or I simplified fluid flow problems where the time dependency is not there. So then I can say it's a two steady flow. Same way, very basic way we discuss about what are the difference between the laminar and turbulent flow. No doubt, when you have the pipe flow, we'll discuss more details what is the laminar and the turbulent flow. Also, we'll discuss more how the laminar partial differential equations will get for the fluid flow and turbulent flow. So more details will learn it, but as a concept wise, as the terminology wise, I just introduced to you. More important, we are you try to understand it, which is called no slip conditions. That's what is the fluid flow is very interesting for us. So whenever you have the flow passing through in a solid surface, so the solid surface, if it's at the rest, the fluid particle close to that solid surface will be the velocity of that fluid particles will be the 0. If that surface is moving with the velocity v, you will have the same velocity of the fluid particle attached to that, very close to that surface. So that's what is called no slip conditions. That's what we have highlighted, because the conditions will be thoroughly discussed in next a series of lectures, that how the fluid mechanics problems are really unique when you apply no slip conditions. Very detailed way we discuss about the basic equations, which is Newton's laws of viscosity. Very simple form with experiments and what is the relationship between shear stress and the strain rate, and few of the questions you have from how that relationship would go to. So basically, if you try to understand with a very simple experiment conducted by Newton's established with a a series of approximations that shear stress causing in a fluid having a linear proportionality to the shear strain rate or the velocity gradient. So this is a lot of simplifications are there, and these are the assumptions also we'll discuss when we have fluid kinematics, non-Newtonian fluids. All will discuss it, but it's the basic levels. We are talking about what is the relationship between shear stress and shear strain rate. That's what here very simple diagrams giving a relationship between shear stress
Subashisa Dutta is currently unavailable. Please leave a message after the tone. When you have finished, please hang up or press
Can you hear me? Okay. So as I was discussing about that, how this microscopic point of view of fluid mechanics and the microscopic uncertainty. This is what I really discuss more details on the class on the video lectures. Please try to look it and reread it and try to understand it, that when you have the sampling volume is too large, and the average density what we get it from the sample volume, that whenever it doesn't represent actual density at the center of the sampling volumes, you get it the uncertainty. That means density can have the variability. So that what is microscopic uncertainty. So more details you can re-watch the YouTube or look at how things are explained in terms of molecules levels, also in terms of the microscopic uncertainty points. That you can have more details how difference are there. Another questions which we saw is what is the difference of system and mass control volume. The system is a control mass. As you have studied engineering mechanics, you have, which are the systems level. That means you consider a particular mass and you try to apply the conservation equations like linear momentum, angular momentum, energy equations to solve the trajectory and the frictional forces and all the things. But when you talk about in fluid mechanics, we don't go for the control mass. Instead of that, we have an interest over special regions. For examples, here we have a control volumes. So that means a particular space domain we consider is my interest over these to analyze the fluid flow. Whenever you do that, you define the control volumes in terms of control surface. So that control surface can have your very much imaginary boundaries or the real boundary, can define it by this. So you can know it from where this mass inflow will be there, mass outflow is there, and which are the boundary there is no absence of mass fluxes. So more detail of the control volumes, how strategically or very like a control volume sketching as similar to the three body diagrams what you do in engineering mechanics. So in fluid mechanics, if you want to be experts in a fluid mechanics to solve different type of fluid problems, you should have a try to sketch appropriate control volume. Then you apply basic conservation equations, mass conservations, linear momentum, angular momentum, energy conservations using Reynolds transport theorems. Okay. So the basically what I'm telling you is a very much introductions level, because this control volume concept you didn't learn it earlier. So in fluid mechanics we talk about the control volume concept, which is a volume which defines a space and it has a control surface, and more detail no doubt we will discuss in the recorded YouTube materials, or I'll come it in the next month in online interactions. We'll be discussing more about what type of control volume we needed, how to approximate the control volumes, those things we discuss. And mostly the fluid mechanics problems we target the flow analysis techniques. One is a control volume, it's a larger control volumes. Or we can have an infinitely small control volumes, which we call it a differential analysis. Or we do the experimental study. I hope you could see that a lot of illustrations we discuss it, how to differentiate between different flow analysis technique like integral analysis, differential analysis, and the dimensional analysis. And we have a very basic laws, mechanics like conservation of mass, linear momentum, angular momentum, for first law of thermodynamics. These are things I just introduced to you. So that way you can look it, and we try to make it a very holistical way to try to address the fluid mechanics problems, either in computational methods, analytical methods, or the experimental methods. This is what the basic definitions of streamlines, path line, and stick lines. Please remember it, the streamlines when you were drawing it. So a line everywhere that tangents to the velocity vector to a given time instant. So streamline I'm talking about the particular time instance. If I draw a lines and the tangent of that lines indicates for us the directions of resultant velocity vectors at that point. So we discussed about the what is the necessity to have a stream tube, what is the necessity to have streamlines, path line and streak lines, you can understand it. It's a flow visualization techniques you can use to understand how the flows are happening. Fluid at the rest, I think we have introduced with some examples, and also we try to look at because fluid at the rest, fluid statics is a very easy subject. I do believe it. You can understand the fluid static well, and few of the examples which is comes from my GATE or Indian service exams, which is manometers, different type of manometers and all, where we use a very simple concept of finding out the pressures, because in case of fluid, when the fluid at the rest, we have only two force components, is one the gravity force and the pressure force. So that's the reasons we are just equating the gravity force, okay, and that's what also we follow the Pascal's laws. So the basic concept, I think I discussed more details how to get the pressures and how to get the use the manometer to measure the pressures at different points. And very interestingly, we talk about the buoyancy, we talk about Archimedes principles, and we also talk about fluid in rigid body motions, how the fluid motions like this looks like a rigid body motions. So as vector components, we have introduced to that, and you can see how to get the jet or the free surface height variability in terms of rotating part. So these are the things we discuss in a first six lectures. Now, what are the questions I got it? I think partly I tried to, one of the questions we got it that what is the variations of density in microscopic and macroscopic level? I think you look at the figures, what we have discussed more detail, that how the microscopic, because of microscopic natures, the fluid density variability will be so high because of random motion of the fluid particles are coming to pictures. That what we discuss with the diagrams, and macroscopic uncertainty also discuss it. We try to do a solve the fluid mechanics as a volume which is above the limiting volumes, so we can adapt or you can use the basic properties of the fluids like density, the velocity scalar field, the accelerations and other components is a continuous functions. That's the reasons we call a fluid is continuous. That's the basic that as we discuss. So basically, way we consider it doesn't consider it simplified or nullify the distinct molecular structures and molecular motions and random motions and all. So we look at the causative way, a controlled volume which is more than this limiting volume. So all these basic properties what we have, fluid basic properties like density, the velocity, pressures, they are the continuous functions of space and the time. So that's why it's the flow continuum. Temperature dependent equation of viscosity is dimensionally incorrect. I agree on that, because that is the empirical equations are derived from a particular range of the data, and how the viscosity is a function of the temperatures. So as the experimentally empirical equations, so dimensionally it is incorrect. That's what it happens when you have the establish this relationship between the temperatures and viscosity. You will have a dimensionally not correct forms. Okay, that will be also discuss similar type of empirical equations later on. Why does the viscosity change significantly? Doesn't change significantly with the pressures. So more details if you try to understand it, that at the what is the pressure range we are working with. the change of the pressure range. What is the temperature range we are working? Please try to understand it. Uh, the, the viscosity changes of pressure and temperature range, which we are talking about, where we are talking about civil engineering concept. But if you go for a high pressure change, viscosity may change it. But those are the studies we are not doing it. So please try to understand it. Mostly commonly observed the fluid flow problems in our cases. That's what we are highlighting, where the range of the pressure difference are not going to change the viscosity. That's what, as I said it, you can have the uh, advanced level of the fluid mechanics to try to know it. Which are the conditions where you will have the pressure does affect the viscosity. What is the directions of surface tension? I think these questions, if you look at that, depth geodesy emails, that already direction is given it. If you look at it, taking a small bubbles and cutting it, you can see the surface, you can see the direction, which direction is acting. So just refer back to this, our PPTs, look at the directions. I think that's the best things. Why trace on the fluids is not proportional to the strain rate, or not proportional to the strain, not in a strain. I think this is what we have discussed more detail, that how the fluids flows are different than the solids. And with experiments with the Newton's laws of viscosity, which is a very simple experiment, it shows the same things, that the CH stress having a proportionality to the CH strain rate. So those things we can discuss it and try to understand it, how the stress strain relationship there with the solid mechanics and the fluid mechanics. Okay, how to define and explain the Newtons and non-Newton fluid? I think that's what we are discussing. In my PPT said that it is the relationship between CH stress and the CH strain rate. If the linear relationship holds good for a group of the fluid flow problems, then we call Newtonian fluids. Otherwise, we call non-Newtonian fluids. That's what with a sketch we have done it. Which are the conditions? There are a lot of examples are there. You can browse in, like there are books like F.M. White, there are books like Single Simbala. Which are the fluid flow problems we have a non-Newtonian fluids? That's what you can just look it and put a more interest on to learn about non-Newtonian fluids. What is the need for defining the kinematic viscosity? How different does it make the divide by the density? What is so useful about it? It's good questions. But if you look at the dynamic viscosity is a proportionality constant between CH stress, CH strain. It is a proportionality constant. When I have a CH strain rate is one value or unit, that means whatever the CH stress generates, that because of the dynamic viscosity. So if you try to understand it, the dynamic viscosity is a frictional force which contributed by a lot of molecular motions and all. It's what we are getting it. It's a forces. Okay, is a force components for a unit strain rate or unit velocity gradient. When you look at why we have divided by kinematic viscosities, I think more details will go it when you talk about Reynolds numbers, how these two properties were clogging it, and it is easy to different type of flow process, which very basic way I talk about the Reynolds numbers and laminar and turbulence. More details will discuss it, because just have to go up to the lecture level of lecture level, where really you can understand it, what is the importance to have a kinematic viscosity. Could you explain giving detailed examples which clearly outline, and that's what I think is that we have to just you have to weight it, how the Reynolds numbers we use it, and how we are going to solve it. So if you have any questions, I think if you, whether any chat is there. These questions okay. Okay, we got few questions last minutes about this total head Bernoulli equations. I think these are the things we'll discuss it as we are going to discuss about the Bernoulli equations, because anyway, Bernoulli equations things it's not for these live sessions, but as will come the Bernoulli equations more details. You just watch the YouTube materials, and when Bernoulli equations live sessions will come, I'll take care of these questions to answer it. Any other questions are there? Yes, I think there is. We don't have any YouTube questions now. I think students you can just ask few questions in YouTube chats. How many students are there? 9. Okay. Is there any questions? Hmm? Yes, please close the session. There is no questions. चलो चाय पी के फिर दुकान शुरू कर सब सुने वो खाते